4.1 Anti-differentiation, Part 2. Find the general solution of the differential equation and check the result by differentiation. So dr over d theta equals pi. To find the general solution, we just need to integrate. What they're asking for a general solution is that family of solutions that includes the c. So we want to integrate both sides. But this left side doesn't really look like what we're used to. So before we integrate, we want to separate the variables. So dr divided by d theta. Usually we just think of this as one derivative, but we can multiply by d theta, think of those variables as separate, so that on the left side we'll just have dr, and on the right side we'll have pi times d theta. So now we integrate both sides, and this integral of dr, one way to think about it might be the integral of 1 dr. So the 1 is the constant, and remember the integral of a constant is the variable plus some constant. And on the right side, the integral of pi, that's another constant, is pi times the variable, so the variable here is theta, plus a different constant. So if we want to signify these are two different constants, we could call this c sub 1 and this c sub 2. But the two constants together could be merged into one, so if you want to think about subtracting, we'll still get r equals pi theta plus some constant. So if you want to skip this step of putting c here and then subtracting it and just put a c on the end, that's fine. So that would be the general solution of the differential equation. And then it says check the result by differentiating. What's the derivative of r with respect to theta? It's dr d theta. And the derivative of pi theta, pi is the constant, theta is the variable, is just pi. And the derivative of a constant is 0. So our derivative is dr d theta equals pi, and that's what we started with. So I've verified that it is correct. So this is just the verification step here, but this is my final answer here. And that's the general solution. Now if I knew some more information about this function, I could find the particular solution. I could find the value for c. So that's coming up. Let's talk about integrating things that aren't exactly in the form that we can integrate. We don't know a quotient rule for integrating yet. So now we have to rewrite everything in terms of some kind of non-quotient. So let's rewrite this 1 minus sine squared x as cosine squared x. Because 1 minus sine squared is cosine squared. And then we could think about sine x over cosine x times 1 over cosine x. Sine x over cosine x is tangent, and cosine x is secant. Maybe you're more likely to recognize this if we write it in this order. Secant tangent. Remember, an integral is asking you, this is the derivative, what was the original function? And the original function was secant x plus c. Don't forget c. So that's our integral of sine x over 1 minus sine squared x. Another type of problem that you'll have on your homework is if they give you the graph of the derivative, they ask you to sketch the graph of two functions that would have the given derivative. Remember, if we know the derivative, we can come up with a whole family of functions, so an infinite number of functions that could have been the original function. So let's come up with one of them. If this is the derivative, here's where the derivative equals 0. Here's where the derivative equals 0. What's going on in the original function if the derivative equals 0? It means the original function had a max or a min. So at -2, we're going to have a max or a min, and at 2, we're going to have a max or a min. Let's analyze this a little bit more. The derivative here these are derivatives, right? They're all positive values because they're above the x-axis. So if our derivative is positive, what's our original function doing? The original function will be increasing. And then that must be a max, because here, all these derivatives are negative. So my function must be decreasing. And then here, the derivatives are positive. So that means my function is increasing. So at 2, it starts increasing. So that's one possible example of a function. As long as I have a function that's increasing until -2, decreasing until 2, and then increasing again after 2, it will match this. It will be in the family of functions. So I could have a function that goes up to here, and then decreases, and then increases. So here are 2 examples of functions that would have a derivative that would equal this. Solve the differential equation. A differential equation is an equation that has a derivative in it already. When they say solve the differential equation, what they want you to do is get to the original function. This example gives us specific values for the original function and for the first derivative. So we're not going to find the general solution, we're going to find a particular solution. So when we integrate, we're going to use c, but then we're going to use this information here and here to find the values of c, the value of c. So we're starting with the second derivative. If you integrate the second derivative, what do you think you end up with? Yeah, that should be the first derivative, right? All right, so what's the integral of x squared? So we're going to integrate both of these. So the first derivative will equal, you add 1 to the exponent, divide by the new exponent, that's the power rule, and then plus c. So now we've got a function for the first derivative, but it's a family of functions because it could be, c could be anything. We do know that x is 0, when x is 0 in the derivative, that the y value is 6. So if I put 0 in here, that should equal 6. So then 0 cubed over 3 plus c equals 6, so c must be 6. So now I know my derivative, my first derivative, the function actually is x cubed over 3 plus 6. So now it's not a family of functions, it's the particular function. I want to get back to the original, so I want to integrate this. The integral of the derivative is the original function. Add 1 to the exponent, and divide by the new exponent. I already have a 3 in the denominator, so 3 and then another 4 in the denominator is going to be 12. The integral of a constant with respect to x is 6x, and then plus c. Always remember c. Now they give us more information. If x is 0 in the original function, the y value is 3. So if we put 0 here and 0 here, that should equal 3. So then c must be 3 in the original function. So my original function is x to the 4th over 12 plus 6x plus 3. So we're just working backwards from the second derivative to get to the original function. That's what solving a differential equation is. And there's your homework. So we skipped 5 and 7 yesterday, do those today, and then 35 to 65 odd, skip 51, 53, and 55.